Turn dark. Yes. All right. All right. So it took a while, but it's working. All right. So notice that we have kind of like an alert, right? Exclamation point. Woo! Get my attention. So again, example 3 is calculated permitted, but it's going to be kind of an exceptional case. What to do to circumvent some type of inherent problem. So it says calculated is permitted but discouraged until absolutely necessary. Okay, I got it. Find the length of the curve of y equals cube root of x on the interval from -8 to 8. All right, so quit reading. Let's go ahead and do that. The cube root of x is one of our parent functions. Should be. That is the inverse of x cubed. Okay, cube rooting number. That's the one that comes in like this, and like at the Olympics and some of the half pipes, it goes vert right there, and then it comes out and does that. And if we're looking at the integral from -8 to 8, here would be -8, it would be +8. So it's very, very easy to see what it is we're actually trying to find. We're trying to find that length right there. But does anybody see any problem with that if we actually try to find its length using our formula? The second derivative doesn't exist at what point? 0? And neither does the, you said second, right? And neither does the first. Good. So you're working backwards. The 100th derivative doesn't exist at 0, and therefore neither does the 99th, nor does the 98th. Yeah, all the way back to the first derivative. Okay, good. Way to go. So remember, our equation relies on the first derivative, okay? Or our formula relies on the first derivative. So if you were ever integrating through an interval where the derivative is undefined, like you have a cusp or a vertical tangent, it's not going to work. It's not going to work at all. You could. That's a good idea. Because of the symmetry, you could integrate from 0 to 8 and then try to find that and double it. But guess what's going to happen when you try to evaluate it at 0? It's still going to be bonkers. It's still not going to work. So that was a good idea. I like that because of the symmetry. Even though it's an odd function, the lengths are equivalent. But because we still have 0, it's not going to work. But here's a way to get around it. If I were to take this graph and reflect it across the line y equals x, anytime you reflect the graph across the line y equals x, you get the what verse of the graph? Yeah, good, the inverse, okay? So let's go ahead and list the actual points down here. This point is -8 comma cube root of -8, which is -2. This point is 8 comma cube root of 8, which is 2. If I reflect it across the line y equals x, I am going to get the graph of x cubed, which looks like this. It now has a horizontal tangent at 0 instead of a vertical, and it does that. And now the point -8, 2, what happens to ordered pairs when you find the inverse? They switch. So now this would be the point -2, -8, and then symmetrically over here, this would be the point 2, comma 8. Now whenever you reflect something across a line, including the line y equals x, it's called a rigid transformation or an isometry. You don't have to know that word. But what that means is we don't change the length of the curve. The length of the curve is preserved. So we can kind of redefine the problem. Finding the length of the cube root of x from -8 to 8 is now equivalent to finding the length of the curve of x cubed. Let me go ahead and write that. From -2 to 2. And now we're not going to run into a problem because what's the derivative at 0 now? 0. What? 3 minus 2 minus 1. Yeah. 0. Good. I like your style today, Katie. All right. So let's go ahead and I'm just going to set it up. I'm not going to evaluate it. Y prime is 3x squared. So here's the length of the curve. It's going to be the sum of the infinitely thin and infinitely many line segments from -2 to 2 of the square root of 1 plus the derivative squared dx, and that's 3x squared. And then you can evaluate that. I don't think this one's going to be able to be done with the calculator because you're going to have 1 plus 9x to the 4th, and I don't think we could do that. So this would be a calculator permitted one, so you could type that into your calculator. Now, if you had to do it by hand, you could use the little tip that you said, right? Even though it's an odd function, we can integrate from 0 to 2 1 plus 9x to the fourth. I'll simplify, and then double it. So doing it by hand, this might be advantageous because evaluating something at 0 is typically a little bit easier than evaluating it at -2. So Andres was good to at least recognize the odd function, but still symmetrical in distance. All right, so that's how you can circumvent a vertical tangent. Just look at the inverse, it becomes a horizontal tangent. All right, absolute value alert, another one. Woohoo, calculator permitted. And again, I'm leaving the rest of you this to evaluate on the calculator as a personal exercise. Find the length of the curve of y equals x squared minus 4, absolute value x minus x from -4 to 4. Crap. All right. I know I need the derivative, so that's going to be 2x minus, minus 1. Whoa. Okay. How are we going to take the derivative of the absolute value of x? I can think of two methods. Not doing it, yeah, and saying we did, right? That would be the third method. What? Yeah, that's probably the easiest route. Using the identity, the absolute value of x is the square root of x squared. In that order, right? In that order. So let's see what that would look like. That'd be y equals x squared minus 4. Now, instead of calling it the square root of x squared, I'm going to call it x squared to the 1/2 power. Same thing, minus x. Now, here's where you have to have a high emotional quotient and a decent short-term memory. You got to come over here and see x squared to the 1/2 and say, ooh, that's x. But not really. Leave it like that. Don't simplify it, right? Because you're going to want to simplify it. It's like, I could do that. But don't. Leave it. All right, so now we're going to use the chain rule when we get there. Y prime is 2x minus chain rule. 1/2 times -4 is -2 times blob to the -1/2 power times the chain rule, the derivative of x squared, which is 2x. Then minus the derivative of x is 1. So let's see if we can kind of tidy that up a smidgen. That's going to be a 2x minus, I have this 2 times that 2x, which is minus 4x. And then everything else goes back to the bottom. X squared to the -1/2 is really the square root of x squared in the denominator minus 1. And now, hey, what is the square root of x squared? It's the absolute value of x, so we can now call it that again. So now we have the derivative, and that was the easiest way to handle the absolute value of x, okay? And once you have the derivative, which you always have to find by hand, so even on a calculator question, you're looking for the symbolic derivative, not a numerical derivative, so that calculator is not going to help you there. And now we can say the arc length is going to be the integral from -4 to 4 of the square root of 1 plus that whole thing squared dx. And that's going to be a 2x minus 4x over absolute value of x minus 1. And this is a calculator question. This one is not going to be able to clean up mathematically, more than likely for you to integrate. But now you could type that in, math 9. And of course, you get the absolute value by doing your favorite math here, math number 1 or alpha window 2 or something like that. I don't remember. But yeah, now you can math 9 it, okay? Math 9 it. Could you do this one from 0 to 4 and double it? Maybe. We haven't checked for symmetry yet. That only works if it's an even function or an odd function. It's a calculator question, so I'm not going to bother it, right? If you did use symmetry and you doubled it on half the interval, does the calculator in the end say, hey, thanks, that was a lot easier, plug it in a 0 than a -4? No, so it's not even worth it. Okay, so finish that as an exercise. The other way, incidentally, to get around the absolute value of x, other than using this identity, is to decompose it into 2 separate functions based upon whether x is positive or negative, and then integrate it over 2 separate integrals and add them together. Yucky, yucky, gross, gross. No thanks. Señor Salta. That's essentially what we did, because if you notice, the derivative of the absolute value of x was x over the absolute value of x. So if you remembered that the derivative of the absolute value of x was Señor Salta, you could have actually have foregone this whole process and just said it was -4 times Señor Salta. Yeah, I'm glad you brought that up. Okay? Or in Colombia, right, hombre trepador, right, as Andres' brother informed me. I've never been, but if I ever go to Colombia, I don't want to call him Señor Salta, if that's not his name there. So anyway. All right, so example 5. It says, sometimes it helps to change all the variables, not in the beginning, and not in the very beginning, but in the very, very beginning. Okay, that's like, before I was born. Let's see. Determine the length of x equals 2/3 y minus 1 to the 3/2 between y equals 1 and 4. Yuck. Okay. Now, I know we don't need to identify the arc that we're finding the length of, but that's just gross, right? I mean, if you wanted to graph it, you'd have to do all this work to solve for y and then plug in your y values to find x values, okay? Don't have to worry about that. If you do this in the very, very beginning, you are not going to change the answer, okay? Let's just go through and change every x to a y and every y to an x, all of them. So this redefines then as y equals 2/3 times x minus 1 to the 3/2, and now we're on the interval between x equals 1 and 4. When you do that, all you're really doing is you're rotating your graph 90 degrees, and that's still an isometry. So it's still going to give you the same arc length, it's going to give you the same area, and it would give you the same volume. Like if it said originally rotated around the x-axis, you would change that to rotating around the y-axis. So that is an option in the very beginning. Just change all the variables all the way through, and that way you don't even have to solve for y. Now this one only works here because we're not really interested in what the region looks like, but it would work also if you wanted to sketch the region. You just got to make sure that you change your intervals and your axes as well to the other variable. Okay, so now I feel a little bit more comfortable. So now let's find y prime. Chain rule, you multiply and you get 1 times x minus 1 to the 1/2 power times the chain rule, 1. Sweet. So y prime is just the square root of x minus 1. And we have our intervals now from x equals 1 to 4, so the arc length is going to be the integral from 1 to 4 of the square root of 1 plus the derivative squared dx. We're changing everything, and then I'll put the square root of x minus 1 there. All right, so from there, if it were a calculator question, math 9 it. If it were without a calculator, let's see, I think this one might be able to go a little further. That's the square root of 1 plus x minus 1, and your 1's will cancel, and so you're just left with the integral from 1 to 4 of the square root of x, which is known as x to the 1/2. So that one does boil down to something that you can easily integrate by hand. And because I know y'all know how to do that, we won't do it, okay? So just another tip. If you don't like any of the variables in the very beginning, change them all. Just interchange everything. Change axis of rotation, change intervals in the equations, ordered pairs, change them all, okay? And you'll get the same answer, okay? All right, now here's a little hint. And again, this is probably not going to be on the AP exam. This is just stuff you might, again, encounter in a cornfield when the crow flies up and asks you. Because they love calculus, they're just not real good at it. It says we also need to be on the lookout for not so obvious perfect squares. Like if you look at a circle, you're like, is that a perfect square? It's not real obvious. No, that's a perfect circle. Okay. Let's see what that means. Find the exact length of this. X equals y cubed divided by 6 plus 1 over 2y from y equals 1 to 2. Oh, everything is solved for x again. I don't like that. It's the very, very beginning. We haven't started. Should we do what we just did on the previous one? Would you do what you did on the previous one? Just write crap? I'm going to go ahead and change the variables in the very, very beginning. So I'm going to get y equals 1/6 x cubed plus 1 over 2x from x equals 1 to x equals 2. Now I feel better. All right, so we're going to need the derivative. So let me go ahead and rewrite that second term. That's 1/6 x cubed plus 1/2 x to the negative first. There's no reason to bring the 2 to the top. Just bring the x to the top. All right, so here we go with the derivative. Y prime is 1/2 x squared minus 1/2 x to the negative tooth. What is a negative tooth? It's a tooth with a cavity. Okay, I'm going to go ahead and clean this up before I plug it in. That's 1/2 x squared minus 1 over 2x squared. Okay, so now I have a pretty derivative. I have my interval of integration. I'm ready to go with the arc length. So L is the integral from x equals 1 to 2 of the square root of 1 plus the derivative squared dx. And that's 1/2 x squared minus 1 over 2x squared. Okay, now this one says to find the exact length. That means no calculator. All right. Who needs a calculator anyway? I do. Well, we got the square root, so maybe this whole thing is the inside function. Is the derivative of that on the outside of the radical, or maybe only off by just a constant? No way. No way. Because the derivative of that's going to be 0 plus 2 blob to the first times the derivative. Ooh, no way. So, gosh dang, what to do, what to do, what to do. Listen to the problem. It'll guide you. Square me. Right? Square me. That's really all we can do. We can't distribute anything. We can expand it. So I'm not sure if this is going to bear any fruit. I'm not sure if it's the right thing to do, but you know what? It's doing something. If I see a path, I'm going to take it. If it ends up being a dark alley with gangsters at the end with knives and guns saying, you want some of this? I'll be like, not today. And I'll turn around and go back. All right? But I'm going to venture down and explore. So remember, to square a binomial quickly, it's square, multiply, double, square. Square, multiply, double, square. So if I square the first, I get a fourth, x to the fourth. If I multiply, notice your x squareds will divide out, and you're left with negative 1/4. Negative 1/4 then doubled is negative 1/2. Then we square the last, and it becomes positive 1 over 4 x to the fourth. Positive 1 over 4 x to the fourth. dx. Okay, sweet, sweet, sweet. Hey, I spy like terms. Do you? I can do something else now. I don't even know what this is going to do, but I can do something else. So 1/4 x to the fourth, 1 minus a half is positive 1/2, and then plus 1 over 4 x to the fourth, dx. Now I'm looking at that saying, okay, it's still not a pattern recognition U sub. The derivative of the radicand is not on the outside, only off by a constant. So, here's what I'm thinking. I kind of have a little bit of a deja vu feeling. Remember we started with that, and when we expanded it, we got that. Yeah? Square multiply double square. The expanded version looks a whole lot like what we currently have here. The only difference is that was a negative 1/2, and now we have a positive 1/2. So if we work backwards, the 1/4 x to the fourth minus a half plus that, it factored into a perfect square, right? A binomial squared. Maybe that factors also back into a perfect square. I don't know, but I'm going to try. So here's how you would try it. Put blob squared. Go ahead and set up your template there. If it's going to work, this is what it's going to be. The first term is going to be the square root of the first term. What's the square root of 1/4 x to the fourth? 1/2 x squared. The last term is going to be the square root of the last term. What's the square root of 1 over 4x to the fourth? 1 over 2x squared. And the sign should be the sign of the middle term. Now, when we square, multiply, double square that, we know the first term squared and the last term squared gives us that. All we've got to do is check to see if the middle term works out when we multiply and double. If I multiply these two together, the x squareds divide out, and I get positive 1/4, which when I double gives me positive 1/2. Oh, yeah. That was a not-so-obvious perfect square, but it was a perfect square. And so there was a hint in the problem itself that helped you recognize that. It's like a easy Jeopardy question where they give you the answer in the question, but really it's in reverse. They give you the question and the answer, because in Jeopardy you have to answer the question. Now, why is this important? That turns into this. Quantity squared, square root of, is just the radicand without the square. And if I write it like that, now it is by hand a simple dimple. I don't know if I've ever said that in my life. It's a simple dimple power rule problem, right? 2 terms. Add 1, divide by 3, so 1/6 x cubed. Plus, add 1 to get x to the negative first, negative 1/2 x to the negative first. Evaluate it from 1 to 2. There you go. Will that kind be on the AP exam with the not-so-obvious perfect squares? Probably not. But again, there's that rare but still possible cornfield possibility. All right? Tomorrow we're going to finish. We're going to look at the application, example 7. And this is something that is fair game for one of my tests or the AP exams. So that won't take long. Then we're going to roll right into the next section. So be looking for the key to 6.3 on the website tonight around 5 o'clock. I'll finish it and I'll post it as soon as I get home. 5 o'clock, the key to 6.3 will be posted. Maybe refresh your browser, but it should be there. All right, perfect timing.